Yeah, so one thing is that Siddharth had a last minute thing, and so because it was hard to reschedule, Sriram is going to separately present to Siddharth day after tomorrow, I believe, and then so I think we're going to have the proposal today itself, but he won't be, Siddharth won't be here, but Sriram will present to him separately and then deal with those comments. So that's where we are. So yeah, I think Sriram is going to present his PhD proposal. So there was a written comprehensive that already the answers were sent a while back. And I think unless you have any objections from the committee, I would suggest that we let him present the proposal, and then we can ask questions both about the proposal and the comprehensive after the presentation. Is that okay?
Yep.
Okay.
It's okay.
Okay.
With me.
So then you can go ahead, Sriram.
All right. Thank you. Hello all, thank you for attending my proposal defense. I'm Sriram Gopalakrishnan, and I will be presenting my research on how we can improve solutions to sequential decision-making problems that affect humans by considering our cognitive limitations in the problem formulations. So why is this an interesting research direction? As automation gets more sophisticated and the performance improves, it paradoxically will place a higher demand on the humans involved around the automation. This is called one of the paradoxes or ironies of automation. And my focus is to consider that human involvement into the problem formulation and improve the solutions that affect or define the human behavior for these tasks. And as we see automation getting adopted in high-stakes situations like criminal justice and air traffic control, the emphasis on modeling the human in the loop increases all the more. And here is an example where ignoring the human in the loop can have disastrous effects, where the entire Dutch cabinet had to resign because their tax authority was using a self-learning algorithm that had learned to categorize people who are immigrants or not citizens as more likely to be putting fraudulent childcare claims. And as a result of this, many families were forced into ruin. The human in the loop in this situation was just over-relying on the self-learning algorithm and kept stamping fraud. So this is a case where there was a simple policy for the human in the loop to check the decisions made, disaster could have been averted. So in response to the notion AI is going to do everything, there are some roles where humans will stay involved in the loop. One instance of that is the human as a out-of-the-loop operator, or OOTL. What this means is when the AI fails, can the human operator, fail-safe operator, take the system into a safe state from which things can be recovered? Another role would be as human oversight, like in the Dutch tax authority we saw earlier, which is likely to become a legal requirement as such situations improve in number. There are also automation limitations that would need to be supplanted by human abilities, be it in how dexterous they are in surgery or the human coordination around automation. So there are still many roles in which humans will be involved, which makes it all the more important to model the human into these problems. So what am I doing for this? My research is to focus on a set of sequential decision-making problems and study how human involvement can be improved. And there are two major approaches I take. One is using a task proxy, which is that component of the problem that places the highest cognitive demands on the human in the loop. I also use problem-specific human models to incorporate the human limitations into the computation. And finally, when proxies are used, we also do human subject studies to evaluate these proxies. So I'm going to first talk about how humans can be involved in sequential decision-making problems, then the components of cognition associated to sequential decision-making problems. And finally, I'll discuss the set of problems that I looked at for this. Now, when humans are in the loop, they may be in a passive role as an observer or consumer of explanations. So they may just look at a behavior and say, okay, I like this behavior, or this is explicable. This is more of a passive role, which I'm not focusing on. I'm focusing on when the human plays a more active role in either planning with the automated system or executing a policy computed either as a single agent or as part of a team. And with respect to these active roles, I looked at 5 problems which tackle different parts of human cognition. I will go over 3 of these problems in some detail, and in the interest of time, I will go over the remaining 2 in an abbreviated form. So what are the components of human cognition, at least with respect to sequential decision-making? For this discussion, we will consider the components as performance effectors, attention, learning memory, and inference. Now, while I do treat them as separate categories, as you might imagine, they are all deeply intertwined. For example, stress affects attention, which in turn affects how well you learn or recall, and what you recall affects the quality of inference. So while all of these are coupled together, in a lot of problems, we can discount some components over the others. For instance, if we assume that the human has a memory aid to recall a policy, we can discount memory as a concern and focus instead on, say, inference. And for each of the problems, I will highlight what aspects of human cognition are pertinent. I did an extensive related work review. Unfortunately, I can't go over all of it in this shorter presentation. Please take a look at my proposal document if you'd like more. But the takeaway that I want to share is that general human models that decompose into a planning and reward structure, either by assuming, say, noisy rationality or finite memory, these aren't a cure-all for human modeling. In fact, this paper by Armstrong and Minderman showed that such decompositions or approximations on inference can lead to arbitrarily high regret. And the solution they propose is that we need to make normative assumptions on human behavior, which translates to problem-specific assumptions on how humans act. For instance, is the human risk averse? How are we modeling humans' response to risk? These are very specific assumptions that we need to consider based on the problem. And this is something we do in our work through the problem-specific human models, as well as the proxies we choose. And now I'm going to talk about some of the problems I've looked at for improving human involvement. We'll first talk about how we can compute policies for humans in problems that can be represented as Markov decision processes. In this, we will look at limitations in human inference and how humans respond to uncertainty. Now, the reason I was interested in this problem is that when we are faced with uncertainty, unlike a, say, automated system that can compute, prior and posterior distributions, we may have different responses. Our response to uncertainty may result in delays or take extra actions to try and resolve this uncertainty. These are the assumptions about behavior that we're making specific to this problem. And because of this uncertainty, we may also incorrectly identify the current state of the world and execute the wrong policy. So what we do to tackle this problem is we model the human state inference and how they respond to uncertainty, use this model while computing the policy through either a heuristic method using policy iteration or a branch and bound method, which gives us the optimal policy. Now, I say policy iteration is heuristic here because human uncertainty actually turns the deterministic policy into a stochastic policy and the MDP into a partially observable Markov decision process. So what we're really doing is computing a reactive controller for the human. So what are the steps involved when a human executes a policy? First, the human observes a state and tries to determine what that state is. They may be uncertain, say state S1 could be confused between S1 or S2. And this uncertainty may lead them to take extra actions to try and resolve it. And then based on their best guess as to what the state is, they'll follow the policy computed to the human. We are making the assumption here that memory is not an issue, either that the human has perfectly memorized the policy or that the human has a memory aid. And so we are discounting memory as a problem. Instead, the cognitive demand or the limitations is during state identification. To help build some intuition about this problem, let's consider this example of a warehouse worker, where the human is packaging orders into boxes of different sizes, like a small, medium, or large box. A set of orders that needed to go into a large box might be confused with a medium-sized order because it's at the borderline. And this uncertainty could result in the human taking the wrong action, or they might try to resolve this uncertainty by looking at the largest object in the order, say looking at the keyboard and seeing, is this going to fit in the large box or medium box, and try to resolve this uncertainty before acting. These extra sensing actions have a time cost associated to it, so it's not free, and we need to incorporate it into the policy. They may also have to decide if bubble wrap is needed or not for different products. So here's an example where humans are still involved in the task, and the policy we choose should consider how they confuse different order sizes. Now, how are we formalizing this problem of computing the policy in an MDP? This is actually a POMDP. We're using the standard terms of state, action, transition, reward, and discount factor. But we also consider what states are likely to be the initial state probability, as well as the human model, which I will talk about shortly, and this parallel set of states, which is an important part of our approach. In our framework, we consider that when the human takes an extra sensing action or a policy outside the MDP actions to try and resolve uncertainty, the state transitions to a parallel state, which has exactly the same dynamics as the original MDP state, but the human's likelihood of state inference is updated. So we're effectively folding the updated knowledge of the human into the state space. So what is the human model that we're using? Now, in this problem, rather than trying to evaluate the human over all possible policies, we focus on the proxy task of state identification, because that's what the human really has to grapple with, correctly identifying the state. And once they do that, they're just following a policy. This is the benefit of using a reactive controller. Now, the human model in this setting is defined by these four terms. There's the probability of state inference, PC, which tells us how likely the human is to infer state S1 given S2. So in that warehouse worker example, how likely are they to infer that a particular order is a medium-sized order when it's really a large order? The other probability term, PU, captures the probability of inferring a possible set of states given a true state. This is, we're trying to capture the uncertainty in the human's mind. So if the order is a medium-sized order, how likely are they to think that it's small or medium or large? So these two terms tell us about how likely they are to infer different pieces of information. Now, the psi terms, psi 0 and psi 1, capture how they respond to this uncertainty. Psi 0 is the likelihood of the human taking extra sensing actions regardless of their inference. And psi 1 is how likely they are to try and resolve uncertainty. Say if they infer two states, how likely are they to resolve that uncertainty or just act on their best guess? All of these terms come together in this equation. I promise I'll be gentle about describing this equation. This captures the likelihood of the human taking an extra sensing action, which is A plus, to try and resolve uncertainty. The probability of the human taking this extra sensing action is determined by the bias or baseline likelihood, psi 0, which is state specific. So for example, they might 5% of the time, they might take extra sensing actions for medium order states. Other than this bias likelihood, the likelihood of taking an extra sensing action is determined by policy differences in the possible set of states. So let's focus on the second line. The red box, the PU term, tells us how likely the human is to infer a set of possible states. If the policy is different in these possible states, then they are more likely to take an extra sensing action. That's all this equation captures. Now, of course, they're not only going to take extra sensing actions, they are eventually going to take policy actions as well. And the probability of the human taking a particular policy action depends on the likelihood of them inferring a particular state, which is given by the PC term highlighted in red, and what that policy is for the state that they inferred. Now, as mentioned earlier, the deterministic policy we give to the human, which maps states to actions, becomes a stochastic policy because of their inference limitations. And that's what this equation represents. Now, given this model of human behavior, we compute the policy for the human using two methods, the greedy policy iteration method and a branch and bound method. The policy iteration method looks at the policy change in all states that gives us the greatest improvement in policy value. It is not optimal since this is a POMDP, so we do need to do some random restarts in order to get better policy values. The branch and bound method does give us the optimal policy, but it's only suitable for smaller state spaces. It utilizes a novel upper bound on the policy value during the search. And we also order the states in an intelligent way to prune the search space quickly. So for example, states that have higher rewards, those policy decisions will be made earlier in the search process. For our computational experiments, we did experiments on two domains, a grid world domain and the warehouse worker domain that I described earlier. The grid world domain, the lion's share of the reward is obtained when the agent reaches a goal state, and the likelihood of confusion between states is determined by the L1 distance between the current positions. For our experiments, we varied the reward or costs associated to actions as well as the discount factor. In these results for the warehouse worker domain, on the y-axis, we have the normalized value, normalized by the optimal policy value discovered by branch and bound. This is the value for the heuristic method. And we do 10 random restarts to see how the best policy computed by the heuristic method is. And in all cases, we do see that the heuristic method does find the optimal policy value at least once. And when we vary the reward as well as the discount factor, it still is able to find the optimal policy with just 10 random restarts, which is encouraging since the branch and bound method takes a lot longer and is not able to handle larger state spaces. For the 5x5 grid world, we see a similar trend. The variance in value is a lot smaller in this case because the lion's share of the reward comes from reaching the goal state, and changing the reward for the intermediate actions does not have as much an effect on policy value. For the 10x10 grid world results, I'd like to direct you to the second table on the bottom right. Here, the ratio between 0 and 1 is the heuristic method's policy value to the branch and bound's tightest upper bound found after 30 minutes. The branch and bound, unfortunately, could not complete the search process because we were running into memory issues. So more engineering optimization is needed. It's still useful as an upper bound, as it tells us the best improvement we could hope for if we increase the number of iterations of the policy iteration method. We also ran human subject studies to evaluate if our assumptions hold water with actual humans. The states here were represented by colors, and we intentionally chose 2 similar shades of red and 2 similar shades of green to cause some uncertainty and confusion. We presented 2 policies. One is the optimal policy ignoring uncertainty, and the other is a policy that considers uncertainty. And sure enough, when we do consider how humans confuse states, the reward accrued is statistically is greater in a statistically significant manner. So let me summarize this work before I move on to the next work. We considered how human state inference affects policy execution. We modeled their uncertainty during execution, and we presented 2 methods to compute policies for the setting. This will be presented at the XAIP workshop, and the main ICAPS reviews were also encouraging, but they wanted us to make some changes in writings, and I plan on adding a 3rd domain before resubmitting this work to a journal or conference. The next work I want to look at focuses on a different aspect of sequential decision making, which is human and robot motion in a shared space, like in a restaurant or in a hospital. And here we're focusing on attention and inference costs placed on the human during this motion. So when people are moving about robots in the same space, they pay limited attention to the robot. They're busy doing their own tasks. And yet, predictability of robot motion is very important for trust and adoption of this technology. So the approach we take is to make the robot motion predictable from just their current position alone, or what we'll call position-only predictability. We also fixed paths for the robots to move on in order to compute their tasks to help with this position predictability. Now, perhaps this example can help build some intuition. Let's say there are 2 robots helping in a nursing home to bring food and medicine to the patient's room. There's also a nurse moving about in this space, providing critical medical assistance when needed. In the image on the left, the robots can move back and forth from any position along those trajectories. This allows them to go between points of interest on the shortest path. However, their movement is not easily predictable by the nurse based on their current position alone. However, in the setting on the right, there's only one position highlighted by the red dot from which the robots can turn or move in more than one direction. And in this case, it's very easy for the nurse to just look at the current position of the robot and bound where they are going. This helps them decide their own path very easily. So the approach we take is to fix paths or rails for the robot to move on. And this is to optimize for position-only predictability. This idea isn't entirely new. Previously, autonomous guided vehicles, as in this image here, followed a path laid down in magnetic tape. What we're doing here is determining how to compute these paths to optimize for predictability. And the idea we're using from cognitive ergonomics is to minimize the logical branches possible in a behavior in order to make predictability easier. The way we tackle this problem is by taking the space as a directed graph where nodes and edges are dropped to represent path constraints like obstacles in the space. In addition to the graph, we also take in an ordered pair of vertices. These are points of interest and represent each task. So for example, in the nursing home, the kitchen and a patient's room would be an ordered pair to represent the task that the robot has to take food from the kitchen to that particular patient's room. We also have cost cutoffs for these paths. They can't take an arbitrarily long path around the room that might be untenable. And finally, we have task weights. Some tasks are more important than others. For example, delivering medicine is more important than delivering food in the nursing home setting. Given this input, the way we tackle the problem is for each task, each ordered pair of vertices, we build a population of paths. And this is done by finding the shortest path, doubling the weights on the directed graph, and repeating the process to build a population of paths per task. Then with these possible paths, we do hill climbing over path combinations in order to optimize for these predictability measures. And we also ensure that path cost constraints are satisfied during this process. So what are these positionally predictability measures? There are two measures we consider. One is the ratio of vertices to the number of branching vertices. And what this intuitively gives us is the number of steps or the next few steps in the robot's path that the human can predict without encountering a branching vertex. So if this ratio is higher, say it's 7, then on average, the human can predict 7 steps of the robot without encountering a branching vertex from which the robot can move in more than one direction. This would make it, and oftentimes the human doesn't need to know the entire path, just enough to figure out if their path is going to conflict in the next few steps. The other predictability measure is the weighted predictability cost, or WPC. What this does is it looks at the number of branching vertices for every task, as well as the out degree of the vertex. The greater the out degree, the more number of possible branches in robot motion, which makes it harder to predict where the robot's going. Here's an example of a 20 by 20 graph that was optimized using our method on the left, versus if you optimize only for shortest paths. As you might expect, our method reduces the number of branching vertices, but trades off in terms of path costs. In the experiments we did 20 by 20 grids and dropped 20% of the nodes and 20% of the edges. I really went crazy on this number 20. We also varied the number of terminal nodes, and the objective is to ensure that all the terminal nodes remain connected. We also varied path cost cutoffs to see how the performance changes as we relax the path cost constraints. For our hill climbing search, we compared two scoring functions, the graph size cost and a branching vertex cost. The graph size cost optimized for just the number of nodes and vertices, and the branching vertex cost considered the number of branching vertices as well. And the reason we did this comparison is the graph size cost corresponds to a problem in the graph theory literature called strongly connected Steiner subgraph. And if the hill climbing search produced competitive results using that, then it would make an argument for using SCS's algorithms here as well. Unfortunately, that was not to be the case. In these results, on the y-axis, we have the weighted predictability cost, where lower is better. And on the x-axis, we have the experimental parameter that was varied. We compare the graph size cost performance and the branching vertex cost performance. And when you increase the number of terminal nodes, the weighted predictability cost gets worse, which you might expect as there are more number of paths that need to be preserved, and so more chances for the paths to cross. In the pair of graphs on the right, as we increase the optimality cutoff, i.e. we relax the path constraints, the search can do better in terms of making position-only predictability easier. Now remember, with WPC, lower is better. So as the cutoff approaches 5 times optimal cost, that improvement in this measure is seen. A similar story is for the ratio of vertices to branching vertices. except in this case, higher is better. We also did human subject studies to evaluate, to substantiate our intuition about the number of logical branches affecting motion inference. What we did is present two problems, one with two branching vertices, the one on the left, and one with one branching vertex, the one on the right. And we fixed the human path so as to control the experimental variables. And we measured how long it would take for the human to reason about a path conflict. And the problem with one branching vertex took on average 47 seconds less, and this was a statistically significant result. We did within subject studies, and this provides support for our intuition that reducing the number of branching vertex helps with path reasoning. So to put all the pieces together, the way we can make predictability easier for the human with less attention and inference costs is to fix the paths for the task that the robot needs to do, such that the number of branching vertices is reduced. The results show the promise of our simple and straightforward hill climbing approach. This is also a novel graph problem. I have not seen anything in the literature about this. I've also discussed with a lot of other professors on this. And this work was presented at ARMAS 22 as an extended abstract and at the ARMS workshop. The third problem and the final problem that I'd like to discuss in some detail is how to assign tasks for human teams, specifically in the context of office teams. And here we're focusing on the human cost of context switching and our preference for autonomy during the execution of a plan. So unlike with machines, our task switching costs or context switching costs are much more pronounced. So managing it can improve plan outcome times. And especially now with remote work given COVID, central control is not always available, or it may not always be liked. Who likes a boss constantly saying when to start and stop a task? Whether it's an AI or a human, doesn't help as much. So the approach we take to tackle this problem is to assign tasks to agents, agents being humans, along with an associated priority at the start of a plan execution period. And the idea here being, with fewer priority levels, there would be less context switching, and that would be preferable for the human. The problem setting we're taking is office team management. Now, rather than presenting it like a tuple, as I previously did, here we'll go over each of the input terms. The input to this problem is a set of goals and goal priorities. Each goal is associated to a subset of tasks that the human needs to perform, or that the human team needs to complete in order for that goal to be considered completed. There's also a partial order plan that captures dependencies between tasks. And it also contains the qualifications needed for each task, as well as time estimates to do each task, a lower and upper bound. For this work, we assume uniform distribution between the lower and upper bound. The employees also input their availability and qualifications, which are constraints in this problem for determining how they can be assigned to tasks. And finally, we have deadlines that need to be satisfied, a make span, in order that evaluates or determines how good a particular solution of assignments and prioritization is. The approach we take to this problem is using a simulator and search approach. The simulator estimates the execution performance for a given assignment and prioritization. The baseline search approaches we use is taboo search and a workload balancing approach. Workload balancing essentially just tries to distribute the tasks to agents based on their availability. The primary approach is a Monte Carlo tree search, where the actions are assignments and priorities, and the default policy is a random rollout of task assignments subject to qualification constraints. The reward in this setting is the likelihood of goal completion determined from 30 simulations. Now, as you might infer, the simulator is central to our approach, and how the simulator works is important in incorporating the human cognitive limitation. In the simulator, there's a central process that looks at what tasks have had their dependencies satisfied in the partial order plan. Those tasks are then placed on the backlog of the agent processes. These agents then proceed to work on a task, i.e., sit with the task until the sampled time is completed. However, if a higher priority task appears on their backlog, like in this image, if task 3 appeared while they were working on task 1, and task 3 is of a higher priority, it'll preempt task 1 and add an additional context switching cost to task 1 before starting to work on task 3. When task 3 is completed, it'll inform the central process, which checks if any dependencies are satisfied, and the process repeats. So the context switching cost is captured in the simulator. We evaluated our approach on procedurally generated partial order plans. This is a visual example of them, where each node is a task with a lower and upper bound, and we arbitrarily assign goals to subsets of tasks with priorities. And as you might expect, load balancing was the weakest performer because it didn't consider task dependencies. But surprisingly, taboo search was just as competitive and much faster than MCTS. So it may be a better option for a lot of practical use cases. The point I want to highlight with the results here in the procedurally generated experiments is that as we increase the number of priority levels from 1 to 3, highlighted in blue, both MCTS and taboo search were able to improve the likelihood of goal completion within the make span time. This shows that they are leveraging the priority levels to improve outcomes. So to put the pieces together for this problem, when human teams are decentralized and they're executing a plan, one way to attack the problem is using assignment and prioritization. Now, since humans have significant context switching costs, those should be incorporated into the expectation of outcomes. We found that taboo search was competitive with our more involved MCTS search, which actually indicates that we should look for more advanced algorithms for this particular combinatorial search process. But it's a good start. This work was accepted at ICAPS 22 in the main track. And if you'd like more details, please take a look at our paper. In the interest of time, I would like to quickly go over the other two problems in an abbreviated form. The next problem that we're going to discuss is how to trade off policy complexity with policy value. And this is once again in an MDP setting. The focus here is on memory and preference of the humans. Now, to give you an intuition of what a simpler policy looks like, let's take a look at this example in the grid world setting. On top is a more involved policy that may be optimal for a given set of rewards, but the second policy below it is a lot simpler to follow, since the actions just say keep going down until you hit the end and then go right to reach the goal state. This is a sort of intuitive example where you can see the trade-off between policy, complexity, and value. And this is something we tackle in this work. We use a trade-off parameter between 0 and 1 to let the domain designer change how much emphasis they want to place on policy complexity versus value. So how is this policy complexity measured? The complexity of a policy is higher if similar states have different actions. And similar states is determined by how the human confuses two particular states. We did experiments for this in grid world and warehouse work as well. And for details, please see our XAIP paper. And the last problem I'd like to present is on how humans can be involved in co-planning when we're dealing with factored spaces. So the motivation here is that factored spaces can be hard to memorize all the possible features and actions that are possible. And humans are better at processing visual information. So we take ideas from ecological interface design, which tells us how to design complex interfaces. These ideas are used in the design of airplane cockpits and nuclear reactors as well. And we apply these principles to factored space planning. In this little example, the logistics domain with some constraints on what cities and what airplanes are able to move between cities, we embed all the propositions and actions onto a 2D space using force-directed graphs. And then the human can click and indicate sub-goals for the back-end fast downward planner to plot a plan to the sub-goal. And then the human can then click on the next sub-goals to reach the final goal. You can restart planning and look at other possible actions and sub-goals during the co-planning process. Now, with EID, one of the emphasis is to only display information as needed. So if the human would like to know what a set of actions of propositions are, they can just hover their mouse over that and details would be presented on the top left. They can also turn off the actions in order to see just the current state and propositions. These correspond to principles of abstraction hierarchy and display as needed from EID. This work was a system demo and an extended abstract at ICAPS. For the rest of my dissertation studies, I would like to add a third domain for the experiments to the work on policy behavior under uncertainty, as well as a proof for the branch and bound upper bound and submit it to a journal. I'd also like to clean up the writing on the robot navigation graph problem and submit it to a journal as well. During my time, these are the research works that I've been involved in. And my timeline to completion is I hope to submit both the journal papers by August, and I'd like to do my dissertation defense in November. And I'd like to end with this slide that summarizes the work done so far, as well as each of the cognitive components that they tackle. Thank you for taking the time to listen to my proposal. And now, if there are any questions, I'll be happy to take questions and clarify any issues.
Thanks, Sriram. So right now, the floor is open for anybody to ask questions, including the committee members as well as the other people attending. Go ahead if you have any questions.
All right. Please take a look at the papers if you would like to know more details and are question shy right now. But,
yes. Okay. So I think the committee members can ask questions right now, or if they would prefer to wait for the closed session, then we will just excuse all the other attendees at this point if there are not any questions.
Sorry. Yeah, I have a clarification questions I want to ask on the first work where you talk about this P formulation, right? So in that case, you talk about the probabilities of like given the state, probability of the human sensing the state given the given the actual state. I mean, how do you have to learn these probabilities, or do you just provide them as
Right. So we do learn it empirically using the state identification task. So we would test the human agent on a particular state, see what they identify, query them on what the possible states are, and see how often they want to take an extra sensing action given a particular inference. So this model is built empirically. You can use an approximate model by assuming that human confusion is based on the similarity between certain features or L1 distance in the grid world, but it's a lot easier to build an empirical model and perhaps more accurate.
Okay.
Any other public questions? Okay, at this point, going once, twice, thrice. So at this point, we will, the people other than the committee members, please leave the meeting.
All right, I think
Okay.
it's just the committee now.
Okay.
Should I stop and restart recording?
Yeah, you actually should stop recording this part. There shouldn't be any recording at all.
Got it.